Hey guys, welcome back to another episode of Introduction to Computer Networks. This is Polly at NTU. Yeah, I see that some of you like rainy days, some of you don't. Yeah, my take is actually closer to James's. Okay, only on light rainy days, as long as I don't get soaked. Okay, but sometimes, right, when it rains heavily, it's hard. I guess I guess it's not bad at all, right? So after many sunny days or cold days, you get a warm day. After many sunny days, you get a rainy day. Okay, and having some differences is not so bad. Okay, good. You know what? Today we have nothing special to announce, and guys, expect something like this in the Wednesday session, because usually we will announce things that you guys need to pay attention to during the Tuesday session. So let's recall what we talked about yesterday. Hey, we started introducing the performance metrics. Okay, that's how people evaluate whether one particular design running on the internet is good or bad. And yesterday we started talking about the first metric called delay. And towards the end, I introduced a tool, a program called traceroute that allows us to measure the delay, not only from the source to the destination, but also all the routers or all the hubs in the middle. And I see that some of you guys go on the PA server to try to run traceroute. That's great. It's just that the PA server is restricted for access within NTU, so that if you are Googling, if you are tracerouting google.com, then you won't reach a destination there. So what I can do is to demonstrate on this machine, okay, that I'm doing the streaming, how it can be done. And this is a Windows machine. So as I mentioned yesterday, you do traceroute RT only. It's a little bit briefer, the command. And you do the route you're looking for towards www.google.com. Okay. So you see that it will send 3 probes. Okay, and for each probe, it measures the delay to that particular hub, and we'll do this all the way till the destination. Okay, all right. Now let's go on to the first topic, which is quiz 6, okay, where we'll ask some tricky questions about measuring delay, all right? And you know what, we'll stay on the screen and just show quiz 6. You see what's showing on quiz 6 is exactly the output you saw in the example shown in the video yesterday. So this is quiz 6, and this is doing traceroute from CSGW all the way to Oricom France, and this is the exact output you saw in the video. So what I'm asking here is for Q1. Hey, there are 3 measurements for each hub, but you see the 3 measurements, they are not quite the same. In fact, very often not the same, right? 16, 11, 13. Why? Why the delays are different across the 3 probes, across the 3 measurements? Now for Q2, for Q2, hey, look at the measurements to hub 10 and hub 11. Hub 11 supposedly physically farther away from the source, but if you look at the measurement between hub 10 and 11, hub 10 gets 113, 121, 114, and hub 11 observes 112, 114, 112, and you see, this particular delay to hub 10 is just longer than any of the measurements you see to hub 11. How can the delay to a closer router be longer than the delay to the router that's farther away? Sometimes. So know that this is sometimes, right? It's not always. As you see, 113 might be lower than 114. So it's not always shorter. Now Q3 is a little bit more open-ended. What I'm asking you is this: by doing a trace route, you can potentially estimate the delay between any two hops, okay, on the trace. So can you tell me, estimate the delay between hop 3 and 4? Okay, make it a one-way delay from hop 3 to hop 4. And also tell the delay or estimate the delay from hop 8 to hop 9. Okay, and what's important for Q3 is this: tell me your method. Okay, so if you're telling me a number, that doesn't make much sense. Can you tell also how you derive that number? Okay, let's see what methods you guys come up with estimating delay from hop 3 to hop 4 and hop 8 to hop 9. And for Q3, you might find that estimating the delay from hop 8 to hop 9 a little bit challenging to do. You might not feel comfortable using the method that you apply for the delay between hop 3 to hop 4 straight on the delay from hop 8 to hop 9. Okay? Good. So let's go to the discourse space. Wait a minute. It's actually not moving. Very interesting. All right, now we are in the discourse space. You see, Q6 is here. Yeah. You guys have, because Q3 is open-ended, so you guys will get 8 minutes time to work on it, and let's start counting time. So guys, I see some very interesting answers already. So let's see. Team 2 here is saying, okay, for Q1, how come the three measurements are not the same? Okay, because there are three different packets, okay, and they measure the round trip time to a particular hub. As they are doing the measurements, there could be other packets going on the same route and interfering with these guys and increasing the time and changing the queuing delay. So there's an example given. Very good. So they say, it's well summarized, the delay measurement really depends on the current traffic of the network. So there are three probes. At each probe, the current traffic of the network at each probe might be different, and that results in different measurements. So what about hop 10 delay being longer than hop 11? Because maybe one of the times, one of the measurements to hop 10, they experience a higher level of congestion, right? That can happen. And the congestion is so high that it's higher, the delay it incurs is higher than the delay transmitting to hop 11 and back. And Team 2 is very thorough answering this question. Additionally, although both hubs are in France, specific paths taken might involve different geographical distances or network infrastructures. I guess in the videos, Polly demonstrated doing trace route. And in that particular demonstration, you see in 3 probes to a particular hub, the routers for that hub are different. The routers for that particular hub are all different. Yeah, so it can be partly because of different levels of congestion when the probes are being sent. It could also be because that particular probe actually goes through a slightly different path over the internet. Yeah, the specific paths taken by the probes might also result in such a difference. And how they measure the delay between hop 3 and 4 is simply taking an average of the 3 measurements, taking average of the 3 measurements to hop 4, subtract them, and if it's one-way delay, then you divide it by 2, right? And this is, by the way, this 8 millisecond is the round trip delay, because the delay you see is the time the source sends the measurement packet, and the time it receives the measurement packet, so that's round trip. So if you are estimating one-way delay, you need to divide it by 2. And Team 2 here applies the same methodology for the estimation of hop 8 to 9 delay. So average of the 3 measurements and subtracting the 2, and you end up having negative 1.33. All right. So hey, so in this universe, the delay cannot be negative. But if you apply straightforward the method for estimating hop 3 to 4, then you get this. It's weird, right? But then how do you measure the delay from hop 8 to 9? Let's see if any of the teams managed to come up with a good solution estimating the delay between hop 8 and 9. Or all the hops in general and without seeing a negative delay. We decided the delay by taking the average time. Yes, well explained. See the result with negative, it's probably just different routes and congestion. So what do you guys think? How do you measure the delay from hop 8 to 9 or measure the delay from hop 3 to 4 reliably? Yeah, clearly you cannot have a negative delay. You cannot have a negative distance either. Yeah. In this case we are calculating delay. Let's see. So the tricky part is calculating the delay between 8 and 9, right? Oh, interesting. It takes the first pair and gets 5 milliseconds. The second pair is odd because that measurement of 1 to 1 is odd. So outlier, drop the outlier. What do you do taking the statistics course? Yeah, the instructors talk about outliers. So it's going to be a distribution. The more measurements you take, you see higher diversity, right? After you see enough of the diversity, then you are comfortable deciding which of these samples are outliers and which can be included to calculate the average. Yeah, so for the third pair, it's also odd, right? So you get only one measurement. The delay is only an estimate, not actual delay time. Yeah. So I think team 1 here is very articulate. Very good. Yeah, they felt that this is just one measurement. This does not represent the general delay between hop 8 and 9. Yeah, exactly. So guys, now you see a little bit why you take these math courses such as statistics. All right, so yeah, so I guess team 5 takes the same approach as team 2, and I think James, which team are you? Team 5, team 15. Yeah, let's see if there are other teams coming up with something different, such that it's not negative. Here, more probing attempts. Very good, team 5. So it looks to team 5 that it's better to do more measurements, collect more samples before you come to a conclusion. Exactly. Yeah, it's weird. Yeah. 16. Okay. 16 finds something a little bit different from the previous teams. Yeah, the delay is definitely somewhat short because sometimes you see negative values. So the conclusions team 6 can see, given just 3 measurements, is that, hey, hop 8 and 9, very close, okay, and very short. And that is not bad at all, right? So observe from what you, so this is what the best you can get from limited information. In team 6, you get negative values as well. Yeah, very good. Very good. All right, so we don't have the time to walk through all of you guys' solution. For these open-ended problems, what Polly will do is to do the grading after the lecture time. But guys, after seeing some of these solutions, you see some diverse thinking. Guys, learn from each other. Learn from each other. And that's the point of doing these quizzes online, because you get to observe what other people are thinking. Okay, good. I trust that you guys figured it out eventually. Now let's move on to the 2 other metrics, okay? Loss and throughput. Loss is very straightforward. This video is less than 1 minute. Packet loss is a lot more straightforward. You see, it's because the queue is finite in capacity. So in case the packet arrives when the queue there in the router is already full. So you see this full packet here, will need to be dropped. That's why we see packet losses. Now, what we haven't discussed is this, the lost packets. To some application, it's actually okay to have packet losses. If it happened, let it happen. So we would not try to retransmit the packet at all. But in some cases, for some applications, users are expecting the messages arrive fully intact. Then we might need to retransmit. Now, as to which entity in the internet to try to do the retransmission, it's really up to the design. So in some cases, we might see the previous routers doing the retransmission. But in most of the cases, we see the original source, the source end system, is doing the retransmission. Oh, okay. So my Stream Deck is finally working, doing some testing in the meantime. And there was a comment actually on the chat from Louise saying that the negative delay can be a noise picked up by virtual instrumentations. Definitely, definitely. And when the delay is small, the noise can result in a negative observation. Okay, good. And now we move on to the third metric. Now this metric is special. I would like to you guys to recall something that we've talked about, transmission rate. That is to account the number of bits per second a node transmit, okay, out of the device. Okay, so that is transmission rate. Number of bits per second, per second gets sent out. Throughput accounts something slightly different. It is to account the number of bits received, okay, per second by a device. Okay, so here's a video explaining how throughput is different and how one determines the throughput at a particular receiver. Throughput is the third metric, and it measures this thing, the rate of transmitting data all the way from the sender to the receiver, from one end to the other end, and the speed of data is going through the entire channel, entire pipeline. Now, there are two ways of quantifying throughput. One is called the instantaneous throughput, the other, average throughput. Now, the units are both bits per second. Okay. But instantaneous throughput is more that you're measuring the throughput at a particular point in time. You will see that if you measure instantaneous throughput, it will fluctuate depending on the situation of the channel between the source and destination. But if you observe over a longer period of time, then you see that the average throughput is more or less stable. Okay, so the throughput here we're talking about and discuss throughout the rest of the sites will be more the steady state behavior, the stable average throughput, just to clarify. Now let me elaborate the example a little bit more. This is the sender, this is the receiver. The sender is essentially a file server hosting big files here. Let's say the file of F bits is being sent over to the client requesting the file. And so we're talking about just the file download, okay, not the request part. And connecting the server and the client, we have one link, one switch, and another link. So it's a two-hop network. And the link capacity for the link directly adjacent to the server is RS, and S here indicates it's the link to the server. And this guy here has the link capacity of RC, and C indicates this is the link rate for the link connecting to the client. Now, let's consider, okay, such a data pipeline as a fluid pipeline, water pipeline. Then you see I'm drawing, okay, the pipeline's width, the diameter, based on the link capacity, RS. So RC here, let's assume it's larger, then you see a bigger pipe versus RS, smaller pipe. And you can also think about the server here being a what? Okay, a water tank, dumping fluid into the entire pipeline here. Now, it might be a little bit easier for you to imagine, right? What is going to be the pipeline's throughput if you consider how the fluids will be arriving at the receiver effectively? Would it be RC or RS? Well, it's probably not that hard, isn't it? Because the intuition tells you that, hey, this guy here, RS being smaller, will limit the amount of fluid that can travel through. Okay, even though RC is bigger, yeah, the amount of water that will go through here effectively to the receiver is still RS. If it's the other way around, RS being larger than RC, yeah, there could be a lot more water coming in, okay, overall carrying RS throughput, but this guy here being thinner is going to limit the rate of the fluids travel through. So in the end, at the receiver, okay, RC is going to be the throughput. And this guy here and this guy here, the link on the end-to-end path with the smallest bandwidth is going to constrain the eventual throughput. Okay, so throughput here oftentimes is being called the end-to-end throughput to indicate that it's the rate of data being sent from the source, one end, to receiver, the other end. Well, after drawing the data network to a fluid network, you see that it's very intuitive how you derive the throughput from one end to another end. And those scenarios are very straightforward, just two links. Let's consider a case that's a little bit more like the internet, okay? Deriving the throughput for an internet-like scenario. So you see here, we have servers and clients, okay? Data will be going from the servers down to the clients through the backbone, the internet backbone. So for each connection end-to-end, we'll be going through how many links? 1, 2, and 3. So we'll be taking the bottleneck link bandwidth as the throughput. So we'll be trying to get the minimum of the 3 segments. Okay, RC is this guy, RS is this guy, clear. The middle segment, well, if there are 10 links in parallel, then this middle link here, capacity R, will need to be divided by 10, as I'm assuming. The 10 connections are fairly sharing the entire capacity. So the throughput to be formulated is this, minimum of RCRS and R over 10. In practice, however, okay, nowadays on the internet, usually it's either RS or RC being the bottleneck. You see, this is an end system, this is an end system. We subscribe access to the internet through some ISP. So this, usually the rate is low. Just like this, the application service provider, they are also subscribing to their ISP. This is also low. As opposed to the big R here in the middle of the internet, in the backbone, those are usually large. It's just that nowadays, there are a lot more connections sharing the big R. Okay? Most of the time, RC, RS are the bottlenecks. But occasionally, you might also see, when network is really congested, R is not quite enough to allow all the connections demanding services. All right, so in short, the transmission rate is determined by the outgoing link capacity, but the throughput, the receiving rate, is determined by the bottleneck link along the path from the source to the destination. So transmission rate, throughput, although the units they use are the same, but they are two different quantities. Okay. And before we move on to the next chapter, so starting from topic 3, we'll move on to chapter 1.5. Okay. But let me draw you back to quiz 6. There's a very interesting solution. Team 9 here estimate the delay between hop and 9 this way. It calculates the average distance between the two hops, okay, and find out the standard deviation, right? And conclude this: the delay may be less than this range. Yeah, with a high probability, the delay is within this range. Yeah, as several teams above mentioned that, hey, negative, it's not possible, but with limited measurements, chances high the delay is low. There you go. All right, good use of statistics. Now, let's move on to chapter 1.5. Okay, so to start this chapter, I have an opening video. It's about a minute because this is a very special chapter. Nothing technical at all. 1.5, protocol layers and service models. Well, this is a very special section. There's not much really technical here, and the purpose is essentially to explain more. You'll see later in chapter 2, 3, 4, 5. The chapter's title is called Something Layer, Something Layer, Something Layer. Okay. We kind of talk about all these internet protocols or internet mechanisms by grouping them into layers. So chapter 2, we talk about protocols running in a particular layer. Chapter 3, another set of protocols running in yet another layer, and so on and so forth. So 1.5 here is to give you an idea why we kind of classify protocols into layers and what does each layer do in terms of functionality, making sure that the internet operates seamlessly. Okay, so we call that the service model, the internet's service model, or the architecture of how we organize softwares running on the internet. Okay. Yeah, sorry, my stream deck is a little bit awkward today. Let's see if it's gonna work smoother later today. Now, so you see it's non-technical, but it is here also to explain how come the textbook is organized this way. There's an application layer next, and there's a transport layer after application layer, and then network layer, and so on. Okay, so why do we talk about these internet protocols in layers? Okay, so this next video explains why. Okay, because internet is really complex. We somehow need to organize all these terms, okay, contexts, in a way. And layering is just the way we choose to organize or to structure all these softwares or mechanisms we use on the internet. Oh, let's recall all the terms we've referred to since the beginning. Right, we've seen hosts and systems. They're essentially the machines composing the edge of the internet. And then the core of the internet, right? The other one at the center of the internet being a mesh of interconnected routers. And then connecting the edge and the core, we do have these access networks or access links that operates different kinds of physical media running different kinds of modulation mechanisms. Yeah, access network. So these nuts and bolts compose and form the physical infrastructure of the internet. So this is more the hardware side of the internet. But we also talk about that, hey, hardware is not the only thing that makes the internet work magic today. A lot of times we rely on these applications in order to what? To see a page that we are looking information from. Okay, so applications such as World Wide Web email. And these applications, a lot of times, right, it's implemented in a way that there's some part of the application running on one physical entity and then another part running on another physical entity. So if you recall for World Wide Web, there's the client side on the client machine, and then there's the server, the web server running on the web server machine. Okay? And these are client and server side will need to communicate based on a specific rule. Okay? And so those rule forms a protocol. So there's also a protocol for the World Wide Web. Okay? So this is one example of the software on the internet. And there are a lot of these softwares. Okay? And application is just one kind of software, right? So in terms of software, okay, there are a lot more to talk about, a lot more pieces. In fact, the hardware part, and this is a very simplified view, okay, there are also a lot of other hardware pieces as well. In fact, to talk about a complex system like this, we do have a major question to begin with. Okay, is there a way, a hope to organize these pieces so that it's a little bit easier to teach or a little bit easier to discuss? Okay, not just between the senior network engineers, but also for the incoming network engineers and how the senior ones teach the junior ones. Okay. All right. So you see that we need a structure, at least for communication purpose. Mm-hmm. But let's actually go through an analogy. This is air travel. So it's the airplane system where we take a flight and fly to another country, take a vacation and back. So in this air travel example, you will see that it's complex. In order for the for air transportation to work, there are many pieces that need to work together. And there's a certain structure there to ensure that human communication. So air travel is essentially also a communication network. Okay, now what does it transmit? It transmits people. Internet is a communication network, but it transmits data. Okay, so here's the analogy: air travel. Okay, observe. And by the way, guys, this is probably the longest video so far, 6 minutes and 20 seconds. See if you can stick around. Eventually, you will see that it's there's a process. It's complex, but one can actually organize it so that we ensure that it operates efficiently. Let me try to use an analogy, air travel here, to show you that it's kind of important to have some sort of organization, some sort of architecture, okay, to make sure a complex system will work seamlessly. And you will see also air travel and internet. Okay. Air travel to communicate people, internet to communicate data. They're somewhat similar, and therefore the architecture used by air travel is similar to the architecture used by the internet. Yeah, by architecture here, I meant the service model, the way the service operates. Now, recall your experience traveling through air. First thing you do, purchase the ticket that guarantees you a seat. At the day of travel, you walk up to the counter, you present your passport and the ticket number. They will allow you to check in your bag and give you the boarding pass. With that, you go to the gate and they let you into the plane. And then the pilot will be negotiating with the traffic control of the departure airport and decide which runway and at what time the plane can take off. And then for a long time, you're just sitting in the cabin and try to get some sleep. But the pilot is busy doing this, okay, routing the airplane. Okay, so as the plane crossing border of some air control, communications will go on again and making sure that the planes traveling the air, the space, will not collide to each other. And hopefully everything is fine at the arriving airport. Again, pilot talks to the traffic control and find out the runway and the time to land. When the gate is connected and open, we may now leave the plane. Most of us go to the baggage claim to pick up our bag and exit the airport. So it looks like it's a series of steps. Very simple. But if you think about it a little bit more, right? Purchasing the ticket is important so that it guarantees you a ticket. So that when you go to the counter, when you're trying to check in your bag, they recognize you, right? And the base of the recognition is on the ticket number, okay? Acquired here and checked here. And in return, you get a bag number, which is used again here. You get also a C number, which is used again here. So there are still some communication that needs to be done, for example, between the steps, in between these two steps. Okay. So this component here, more closely related to this component. This component here is also more closely related to this component. And this component also connected and related to this component, even though this is at the departure airport and this is at the arrival airport. Okay. So you see that there are components that are related and there are some base in order to communicate between the staff members here and the staff members here. Okay, the mechanism here and the mechanism here. But you see also, for example, baggage check here, well, it has less to do with the pilot communicating with the central control. Okay, you see also a little bit, right? This is a little bit more like the internet core. The functionality is quite different, but these are a little bit more like the edge of the internet, where you're trying to track data. Here we're trying to track passengers and the belonging of the passengers. Okay. And so that it's probably not that hard to see. There's a architecture there, okay, and it's kind of laid out in layers like this, right? This is communication to traffic control, but at the end, communication to air travel on the other end. Communication of air travel, but from region to region to region to another region's traffic control office. Okay, so to regional office, it's just to make sure that the height and the orientation of the travel is correct. Now these involves also runway. So you see there's slight differences between these two layers. Now these three, okay, are more handling the passengers and baggages, not handling the plane per se. Okay, so which gate we get in and which gate we're coming out. So your families and members will know where to go to pick you up, for example, to welcome you back, for example. And baggage here, the number is important. At the destination, you also want to know which station is for the baggage claim. There are usually multiple of them, right? So it's also based on the plane number, the flight number. Similarly, ticketing. Sometimes you need to delay travel, right? So you need to call the ticket office again to try to change the date or change the class, okay? And the reference is always, for example, the ticket number, okay? So for communication, you need certain important IDs, important information there, okay? To communicate within a layer, okay? The claim ticket there for the bag is so that you can pick things up on the other end. But there are also certain numbers. For example, ticket number connects to a bag number. Ticket number also connect to a C number here. Okay, so certain pieces of information might be added there, either to allow communication within the same layer from local side to remote side, or information to allow components across layers on one side to try to relate to each other. Okay. Yeah, so you see, air travel, okay, is a complex system. If any step goes wrong, it could end up being a disaster. Okay, it needs to be well structured to make sure also that it's efficient. So there are layers. Okay, each layer implements a particular function. Okay, a particular subservice. Okay, and so there will be some internal actions, but they will also depend on services or functions provided by the neighboring layers. Okay, from the layers below. Okay, or they might also need to provide supports to layers above. Yeah, so an entity in a layer would definitely work with the other entity within the same layer, but also the layer above and below. But in a complex system, that's all the entity need to work with. Okay, all the other layers that are farther away can be neglected, can be left alone in a way. Okay, so in a way, you can probably see the advantage of operating a complex system this way, right? For a particular task, you know very well, in case there's an issue, who to go to. So layering helps. Hopefully with the air travel example you see, in large complex systems where we have lots of these pieces, it's really good to have some explicit structure so that it's a little bit easier to identify in case there's a bug, which piece the bug is, and to find out what are the related pieces might be partly to blame as well. So having explicit structure, really good. And you see in the air travel example, we have this layered architecture, layered service model. That's exactly what we're using, okay, to manage, to organize internet's operation. And we call that layered service model also the reference model, because we are referring to these pieces on the internet in layers as well. Okay, so it's our reference model for discussion among the network engineers, okay, which you are becoming one as well. All right. So this way of trying to break a large complex systems into pieces, okay, and to define, okay, the functionality of each piece is also called the modularization. All right. So after defining the functionality of each pieces, after finding out the relationship between the pieces, okay, we implement the individual modules functionality. We also implement the interfaces to communicate from module to module. Okay, so that is called modularization. Okay, this is really common. We see in large software systems, okay, because it's a lot easier to maintain. It's a lot easier to debug problems, and it's also a lot easier to improve the system, to move a complex system forward. Okay, because you see, the important functionalities are well modularized. So if we need to change the way we implement the functionality, we can just change it. Okay, and that change does not need to propagate through the entire system across the different modules. Okay, so a change, okay, in a layers service, a change within a piece, a change within a module, okay, can be transparent to the other modules. Okay, because the APIs are already well defined. There's minimum communications required. All right, so it's just like this. Here's an example. If we change the gating procedure and we decided that we let the first class passengers to go last, hey, it's not going to change how the pilots communicate with the traffic control, right, in order to find out which runway to take off. So each module more or less independent, and the communication across modules, across layers, are minimal. Modularization, or layered reference model, layered service model. Sounds nice. Can you think of anything that suggests such a layering is not exactly good? All right, so you see, having these layers or having a structure, it helps making the operation more efficient, and it helps also making the operators to communicate. Okay, so that's what the video 2 and video 3 of this topic is about. Okay, so that was INET service model, internet service model. So you have these layers, okay? And you know what, guys? It's 11:09. Yeah, there's not enough time for us to finish the next videos in order to have a break in a timely fashion. So I had another pop-up quiz today. That's do you like a room left messy or organized? And I see some say organized, some say messy. Messy till too messy. Let's see, it helps me generate random inspiring thoughts. Really? Wow, cool. Often messy, but organized once in a while. I'm lazy. Organized for me, but usually gets okay, Stanley, that's very honest of you, right? Most of the time you want it organized, but hey, there are always things there. So you might not have the time or energy to organize in a timely fashion. Yeah. Needs to be messy in my own way. Brian. Hey, your point is very interesting. Okay. When I was younger, my room is often messy. Hey, I confess. But sometimes when my mom or other siblings come help me organize, I lost track of things. Have you had that situation before? Yeah. So some like messy, but it's a result of that you have lived with a messy environment for a while, I guess. But I guess that also many of you says organized. Okay. Yeah, I guess maybe for the study room, for the library, it's better maintain organized. But for like living room, dining room, maybe it's okay to leave it a little bit messy, looking a bit casual. All right. So you know what, guys? That's very good discussion, and I hope that it justifies how come the textbook organize these protocols. In fact, all the internet engineers organize these protocols and entities involved operating the protocols in this layered fashion. Okay, chapter 2 is in fact called the application layer, right? And then the next transport layer, and then the network layer, and then the link layer. All right, good. So let's take a break, and we'll come back to wrap up chapter 1 and then begin chapter 2. So currently, what I have here is 11:12. Let's resume the lecture 11:22. Right, so we're back. Slightly about 10 seconds earlier than promised, but it's okay. So I just want to talk about the comment from Kenny. Yeah, so there are many of the big airlines now have a network to store their planes so that they can dispatch the airplanes in an organized fashion. Um, Yeah, for example, to avoid a single point of failure. Okay. So it's somehow scattered all around. And they're probably also well scheduled, considering some, with consideration of having some reservation at each hub. Okay, good. And welcome back. So now we are ready to go through the internet protocol stack, having many layers, and they get what? Stacked up. Okay, so these multiple layers or internet protocol stack is what I'm going to talk about in this video. Here's the internet protocol stack, and you see here what I'm illustrating. It's in the layered architecture. The layer at the top is the application layer. So these protocols at the application layers are literally to support the applications. For example, HTTP is supporting the web application. So you do have application processes sitting on the web browser side and another application layer process at the web server side. Okay? And there's a protocol there. For example, a message go out is necessary from the client to request for a web page, right? And that web page will be another message coming back the other way. Well, that's pretty much what HTTP defines. Right? So these messages to control when to start sending and which web pages to send. Transport layer, that's one layer down. Okay, the functionality is essentially to allow these application layer protocols to specify whether these data that I'll be sending through, these data packets I'll be sending through the internet is going to be reliably transferred or best effort transferred. Okay, so this is to administer data transfer from client to server process or vice versa. Network layer protocols, on the other hand, very special. Yeah, all these packets, oh, by the way, packets, when it arrive at the network layer, it's called another name, datagram. So these packets coming from the source, right, needs to find a way to the destination. You see, at the core of the internet, we do have a mesh of interconnected routers, don't we? A router could have multiple connections to other routers. So each router will need to know, which is the right router to forward next so that the packet will arrive at the destination with the shortest distance possible, right? Because you do want the packets to arrive at the destination as soon as possible. So a good routing protocol is to ensure something like this. So network layer, the protocols there are essentially to handle packets being forwarded and the directions of how these packets being forwarded in the core. Link layer protocol. Okay, so these are very special. They work a little bit like, honestly speaking, the transport layer protocols. Okay, transport layer is to handle data transfer from one process to another. Link layer protocol here also handle data transfer, but it's between one network element to another one network element, one network hardware to another network hardware, or a network entity to another. For example, between two routers directly adjacent to each other, there's just one link. Okay, so this might across several hops at the transport layer, but link layer protocol only handles data transfer in one hop. Okay, so it deals with the data transfer very locally within a link. For example, Ethernet is a link layer technology, a link layer protocol. Yeah, so there's a question from Stanley asking about the OSI model. Yeah, it was it was the original internet model, layered model, in fact. But gradually, we kind of just skipped the presentation layer and the session layer. Okay, so what remains are just physical data network transport and straight to the application layer. I've never seen real protocols operating on the internet that does session and presentation. Okay? So I guess when people are building these protocol architectures for the internet, they consider more. But as the internet developed, eventually that we don't see the need of having these two additional layers. So yeah, so it was OSI model to begin with, but we ended up having just 5 layers in the end. Okay, so the internet protocol stack nowadays that people refer to are just 5 layers. Is it possible to connect 2 routers with 2 links, like just to increase their bandwidth? You know what? It's possible. Yeah, you just get get these 2 routers, 2 network interfaces, then they can connect with 2 cables. But you need to configure the routing table properly. And if you want to do load sharing, you also need some extra mechanism. Yeah. For routers, it's very common you see multiple network interfaces because the sole and very important function of the routers are to keep connections with other routers. For the end systems nowadays, we see very often multiple network interfaces as well. For example, you have an Ethernet, the wire cable interface. You might also have the Wi-Fi interface. And these are already 2 interfaces allowing you to connect to the internet. Yeah. One can potentially use both of these interfaces to access the internet. All right, and the last video from chapter 1 is this. So what Polly is going to show you is how the packets travel through the internet in 2 dimensions, vertically through the protocol stack within one device, and then and horizontally across the devices, such as routers and end systems. So this video is a little bit long, 6 minutes, but after the video, you get a really good sense of the life of a packet, okay, as they are being sent from the beginning to the end. With the layered architecture explained, what I'm showing here is the software side of the internet side by side with the hardware of the internet. So where are the hardware in this example? Look, here, and here, and here. So these are end systems, okay? This one is the source, and this one is the destination. You see that at the end systems, the entire internet protocol stack is implemented and running. Similarly for the other end system. But in the core of the internet, you see the router over here, and this is a very special entity, hardware entity. It's called switch. But to be precise, this is the link layer switch. Its functionality is limited. Okay? Unlike router, this is a network layer device that implements the protocol stack from the lowest up to the network layer. The link layer switch is a more limited device. It implements only from the physical to the link layer. Well, then you see how it gets the name. It's a link layer switch. And if you want to be precise, you can also call these routers the network layer routers. Or sometimes we actually call these routers network layer switches. Okay, so both of these entities are doing switching, but doing the switching at a slightly different level. All right, now walk with me and let's see how the data gets passed down the protocol stack, out of a physical entity, and through the network, reaching the destination. The first step is this. Yeah, one particular user typing things up. So at the application layer, this component generates a message. Yeah, a packet at the application layer is referred to as a message. The application layer component will pass the message down. As the message arrives at the transport layer, a header is being appended in front of the message. Okay, because it's appending, therefore, these additional pieces of information is referred to as the header. H stands for header. And this is a header appended by the transport layer, therefore HT. The whole thing together, this packet, is referred to as the segment. So a packet at the transport layer is called a segment. And you see that this header here is very important. This is to allow the transport layer component at the source side to communicate with the transport layer component at the destination side. Okay. So this is a little bit like at the airport. When we're checking our bag, The counter is going to give us back what? The passport, the e-ticket, and what? The baggage claim ticket. Okay, so that baggage claim ticket, that additional information, okay, in order for you to find your bag, is a little bit like the headers. Okay. And now the segment is going to be passed further down to the network layer. And guess what? The network layer component is going to append some more information to it. And that is in the header as well. But this is the header for the network layer, HN. And the whole thing now, the packet here at the network layer is called a datagram. And the whole datagram is going to be passed down further to the link layer. And guess what? The link layer header is going to be appended, and we call a packet at the link layer a frame. So this frame here, now arriving at the physical layer, what physical layer is doing is simply modulating the 0 and 1 bits, okay, onto the physical media. So it's going to go out shortly through the network interface and arriving at the router here. Now I'm skipping the switch here because it's a link layer device. We'll not be able to cover the link layer chapter. So this message is going to arrive here at the router, receive at this physical layer, and the signals gets converted to the digital form. So we restore the original frame back, and that's passed up into the link layer. The link layer at the router is going to examine this header and see if there's any additional function that it needs to perform. When everything is done, guess what? Okay, this header is going to be removed. So only the message with the transport layer header and the network layer header will be passed up to the network layer. You see here, the message is being passed upwards, okay? Because the network layer component of the router still needs to check this, okay, and see if there's something that the network component needs to do at the router. So this is going to be examined, okay, and functionality is performed. Now this part, hey, as this is a router, there's no other layers above. So this is going to be copied over, okay, and stand by there at the outgoing interface. Now before that message go down to the lower layer, the new network layer header is appended. And this one is a datagram. It gets passed down to the link layer header appended. And this is a frame. It goes to the physical layer, bits modulated, traveling the link and reaching the destination. Similarly, the physical layer is going to recover the 0 and bits and give this up to the link layer. This checked by the link layer, and the remaining gets passed up to the network layer. And you see this removed, this part gets passed up to the transport layer. This removed, and this part here gets passed up to the application layer. And here, the destinations processed there at the application layer finally see the message coming from the source originally. So this is how a message travels through the protocol stack and the physical infrastructure, and more protocol stack up and down until all the way up to the application layer at the destination. All right, so that was the end of chapter 1. And we're moving on to chapter 2. Yeah, there's a question from Sam. Why do we call the packets different names at different layers? From what I'm aware of, it's just so that it's a little bit more specific which layer we are talking about. Yeah. And Sherman, offer another nice thing about naming the packets differently. With different names, you know exactly what packet headers there are in the packet, right? Very good. And I can see how long the network delay is. You guys are accessing the internet from how fast you answer the pop quiz just now. All right, good. So that was chapter 1, and it's just the beginning of the semester. It's to give you a very high-level overview of the internet. And now we'll start from the application layer, the highest, the layer that is closest to the users. Okay, so you guys are not yet internet engineers, but you guys are at least the internet users. Okay, so we'll start from the chapter that is the closest to you guys. And the first video, it's also not technical. All I'm doing is just to mention a few applications that you guys are using already. Pollys is definitely using them. But previously, you might not be aware that these are all network applications, internet applications. So here's an inventory of applications, okay, of inventory of internet applications. To make sure that we're in sync, let's inventory some of the popular network applications here. Email, web, nothing more need to be said. They are obviously email and web. Text messaging, Line, WhatsApp, what else? A Google Messenger. And if you guys are watching this from a YouTube live stream, that chat room is a text messaging app. Remote logging. If you downloaded a client to remote log into the PA server, then you're using a remote logging application or remote logging service. P2P file sharing, the most well-known one, BitTorrent. Okay. Multi-user network games. Okay, so this is a more formal way of calling online games. Okay, so some of these online games are running on desktops, going to the game server somewhere provided by the game company. The client can be nowadays running on smartphones. In fact, probably more games people are playing are mobile games. Okay, so the client is on the mobile platform. And then the multimedia applications. Here we have the streaming stored video, and we have the real-time voice. So this is also called the voice over IP. And we have the real-time video. Okay, well, real-time video conferencing, of course, also comes with audio. Okay, so essentially these three are multimedia applications. The difference between this and these other two is that the video is actually a playback video. So the video is already stored in one of the video content server, and when you request it, it is just playing back the video. But for these are the live video being generated as you guys are having conversation, as we are having conversations. So the delay requirement for live audio video is a little bit higher, more stringent. So what do we have as real-time video conferencing apps? Yeah, Google Meet, the one we have standing by here, allowing you guys to call in, is a real-time video conferencing app. So there are other real-time video conferencing apps such as Zoom, Microsoft Teams. What else? Well, Skype. Although transfer audio, it also transfer video. So Skype is also a real-time video conferencing app. So there are many options here. Social networking. Hey, Facebook, IG. One can probably come up with others such as Snapchat. Yeah, so there are just increasingly more of these social networking apps. Search, Google search or Bing. Yeah, each of these is also an application or a network service. Cloud computing, yeah, Amazon AWS, for example, is a cloud service. And that takes us to quiz 7, guys. Yeah. So this is quiz 7. What's nice, Polly being a professor, is that I have access to you guys. So that allow me to survey what the young generations do over the internet. Okay, so this is just to keep Polly in sync with the society. So let me ask you guys, Q1, can you tell me the top 2 network applications you use on a PC or a laptop? The top 2 for Q2, the top 2 for the top 2 application you use on your smartphone, and then Q3, the top 2 games you play, regardless of the platforms. Okay, and for this quiz, I guess it's easy to answer. So you guys have only 3 minutes, and let's start counting time. Let's go to the score first. The score space first. W3 quiz 7. Oh wow, okay. I see some teams posting solutions already. Yeah, 3 minutes. Guys, hurry up. so yeah, this semester I've added a timer for myself. Sometimes you guys' answers are just amusing. I might overspend the time reading them. Yeah, so thank you guys. Very good to know. YouTube, Gmail, and I saw that I think Team 5 spending a lot of time on NTU Cool. You study very hard. Good for you, Team 5. Okay. Yeah. Yeah, I think this, yeah, another team. So Team 16 says Pokemon trading card game. Yeah, I saw some other team, there's a member playing this game as well. And I think the trend is also more that there are more smartphone games that you guys shared with us. Tetris, old-fashioned, wow. Pokemon. Very interesting. Tetris. Dark Soul, wow. Anthony, I have no idea what games you're playing. Thank you sharing that with me. Oh, okay. Team 13 decided that they want to share all the apps they use individually. Very good. BitTorrent, WeChat, WhatsApp, LOL. Okay. So streaming store video, I guess something like Netflix, WhatsApp, WeChat. So I guess WeChat is growingly popular globally. It used to be just the China thing. Risk Online and Super Auto Pets. No idea. Sorry. Excuse Polly about these games. Oh, here's another one. But Pinyu was saying TCG Pocket only. So is this a physical game or a online game? So maybe it's still an online game, right? Instagram. Line. Yeah, the Line is very popular in Taiwan. Messenger, Discord. And Clash Royale does look like a mobile phone game, right? Yeah, many of you play this game, Clash Royale. Minecraft. Yeah, I've seen the game earlier above. Okay, LOL. Well, there's a very high variety of games you guys play. Very amusing. Thank you for sharing with Polly. So this is just my sample of how the popular games and popular apps have changed over the years. Okay, good. LOL? Interesting. Oh, surely a hardcore gamer. Dark Soul. Oh, okay. So, so you guys are also learning about each other. That's good. I bet he played Elden too. Oh, okay. The Elden Ring? Yeah, that game I have heard about. Very good. So, hey, you guys might, eventually make a friend of each other who you don't know previously. Good. All right, so now you guys know. All these are internet applications, network applications, and these are the apps that are making big monies for their owners as well. So, you see, guys, now, starting from this time point, think this way. Think like an app engineer. Okay, so how do you design an internet app? Okay, think this way. So next video, what I'm gonna play is to tell what these internet apps are doing at the sender side or at the client side, at the server side. Okay, so where they are and how eventually you'll be able to design and implement a network app. And this video is strictly just talking about what the network app does. Now, to support all these applications, the principle is quite straightforward. Essentially, we write programs. There involves at least two parties. One program sits on one of the parties. Particularly, each of the programs sits on each of the end systems involving the communication. Okay, so they will be communicating, sending messages over the internet. So for example, web server program sits on the web server machine, browser sits on the client machine, and these two programs send messages to each other, much like this. So we might have a web client here, we might have another web client here, and the web server is down here. And we establish connections like this. So this client's program interact with the server's server program. This client's program interact with the program running on the server as well. Okay, so you see that the server program here needs to be a little bit more powerful, allowing requests from these clients, okay, frequently and potentially simultaneously. So essentially, in order to create these network applications, we design how the messages are exchanged, meaning designing an application layer protocol. Afterwards, we program the softwares. There'll be one part running on one end, the other part running on the other end. So this example here is a client-server application. For P2P, one runs on peer, the other runs on another peer. But in P2P, these two programs usually are identical because they are both peers. Now, what's unique here is this. Applications run only on the end systems. In the network core, these routers, the routers do not run anything particular for a particular application. Okay, so the core devices do not run applications. They do not run specific functions to support individual application. Okay, so applications are strictly on the end systems. So clients, limited devices such as a smartphone, such as a laptop or desktop, are on the edge of the internet. But you see here, servers, more powerful machines, they can be quite expensive. Some of them can be just as expensive as the routers. But these servers are also at the edge of the internet. They are also end systems. Just don't be confused. Okay, so these end systems, there are programs running and exchanging data such that we can perform a specific application or specific service. All right, so the key takeaway is that these network applications run on the end systems. The routers are just passing data. No applications running on the routers. All right, now, hey, my fellow, okay, novel application programmers. There are four very important elements you need to design, okay, or implement, okay, to come up with the working application. So the first element is to decide the architecture, or aka the communication models of all the end systems might be involved for your application. And there are three major models. You've heard about the first two already. First thing we do designing a network application is to decide its structure. There are three general models and we'll go through them one by one. First is the client-server model. In such a model, we have powerful machines we call servers that are always on and running on permanent IP address, therefore always reachable, and sitting in one of these data centers allowing access from users worldwide. Now, on the other hand, we have the clients. These are the devices operated by the end users such as us. So these are the devices initiating communications to the servers. And they are intermittently connected to the internet as we operating these clients are moving around. And so from one location to another location, we'll be using different IP addresses. That is why the clients do not communicate directly to each other, because the IP addresses that each of these clients is using the next moment can be different. So two examples on the left are first, a driver in a car looking up a route to a particular destination, and she could be accessing the Google Maps server. And this can be a student looking up the PA assignment, then this will be the web server of the course webpage. Second is the P2P model. In such a model, there are no longer always-on servers. all we have are just a bunch of these intermittently connected end systems. These end systems will be communicating directly to each other. And we call these end systems peers because they will be requesting services from other peers. They might also provide services to other peers. That is saying that these peers, these end systems, are not strictly client or strictly server, and each of them play equal parts. So peers are a better way to characterize these end systems. This is what's nice about the P2P model, self-scalability. When a new peer joins the network, as they request for services, you will see that the demands go higher. But they bring also computation or storage capacity, right? So we get more resources as well. This is opposed to the client-server model, where there are more clients joining. The service demands will rise, but the capacity doesn't. Now, on the downside, the peers are all intermittently connected. That means the IP addresses are changing all the time. So you can imagine that it can be a little bit challenging maintaining a continuous connection. Third is the hybrid of the first two models, and this is used by Skype, a voice over IP service that used to be popular. And in Skype, the call in between two users, that is done by a direct connection between the two users and systems. So you can see that it's P2P. But to establish the call, you need to find the address of the user you want to call to. And that is done by querying a centralized server. So you see this part of Skype is client and server. And so Skype is under such a hybrid architecture. All right, so those are the three general categories. Later on, you will see in some apps, you might see some app use the client-server model, but then the architecture is not just client and server. On the server side, there might be several levels of hierarchy. And in some apps, still client-server, but there are some level of hierarchies as well at the client side. Yeah, so it really depends on the application. Okay? The eventual architecture can be a little bit more complex than the basic ones. Now, after you decide the communication model, how the entities are connected to each other, then you need to connect them. Okay? The way you connect them is to implement socket and configure the sockets. And let me explain what socket is. And towards the second half of the video, you will see that one of the very important parameters to configure into a socket is this thing called the port number. Each computer on the internet has, or each network interface on the internet has an IP address. And within a computer, computer running a network interface, the processes, we might run many of them. Each of the processes usually have a port number. Okay, so a slightly long video. In a network application, we'll have program running on the client side, server side, or peer side. Okay, and these programs, as they are running on a host, we call it a process. And so what we want to achieve is for these processes to communicate with each other. Traditionally, to communicate two processes within the same host, all we need to do is just call some of the system calls defined by the operating systems that will allow inter-process communication. But for processes on different hosts to communicate, we'll have to send some messages. And this will be done by a socket that we'll talk about shortly. And so the process on the client side will be called the client process, and it is the process that initiates the communication. The server process on the server side will be the one waiting to be contacted. Now, for a P2P architecture, on each of the hosts, we'll have to run both the client process and the server processes so that they can provide services to each other and request services from each other. So socket is this thing that allows the processes to send messages to each other. Okay, think of it as a door. Okay, so the sending process will first shove the message out the door. So the sending process here, shove the message out the door, out the socket. And then the transport infrastructure on the other side of the door here, okay, will then deliver the message over the internet to the socket of the receiving process. And after shoving the messages again through the socket, the receiving process gets the message. So from this line and up, this is the application layer. So everything in this space will need to be defined by the developer. That includes the sending process, receiving process functionalities, as well as the sending and receiving sockets functionality. Now, the socket API is the tool allowing the developer to specify the sending receiving sockets. That includes defining the transport layer protocols to use, as well as a number of other important parameters, such as the port number of the receiving process. The most important parameter to set for a socket is the address of the receiving process. Therefore, you can see that for each process running on the internet, we need a unique identifier. Now let's take a step back. We know already for each host, there's a unique identifier called the IP address. So this IP address will be sufficient to identify a host, but would it be sufficient to identify a process? Not really, because nowadays we see very often multiple processes running on a machine. And so we need something else in addition to the IP address, and that something else is called the port number. Together, they uniquely identify a process running on the internet. Now, some of these processes could be well known, for example, a server process for the web, a server process for email. So they could be running on a well-known port number. So web server is very often running on port 80. Mail server is very often running on port 25. In this example, if we send a message to a web server, gaia.cs.umass.edu, that socket will need to be specified with this receiving address. So the IP address of the machine and the port number the server process is running on. All right, so architecture defined, socket created. What can we do now? We can start sending packets, right? And the packets at the application layer are called the messages. So, what do we do with these messages? We need to define, right, the format and the actions triggered by these messages. And maybe after receiving a message, the action is to generate another message. Now we have socket created connecting processes. We can begin to send messages. But you see, what we're talking about here is general application design. So an application can be a little bit complicated. The server could be providing multiple services. So how do we know, right, when the server receiving a message, the client is asking for service 1 or service 2 or service K? And vice versa. The server could be sending a message back to the client. And how does the client know what is the intention of the server? The messages being exchanged between these two processes need to be clearly defined. So that includes the type of messages. So one may be sending a message for a certain occasion. So there could be multiple types of messages defined for an application. Now use World Wide Web as an example. The client typically sends web requests and the server sends web response. And inside the response that contain the web page the client is asking for. Now, continue to use the World Wide Web as an example. Inside a web request, there'll be some fields, okay, we define. For example, time of the request, browser of the request, or language preferred by the user sending the request. Okay, so there'll be fields like this with the values that will contain in the web request arriving at the server. Server knowing the syntax, okay, of the request message will understand exactly what's going on the client side, and therefore send the most up-to-date web page in the preferred language, for example. Now, we also define semantics of messages because, again, using World Wide Web as example, the web response a lot of times sends back, for example, status. Okay, so this is the status of the request. Now, if the client is looking for an object that's no longer existing on the server, you see very often a response coming back saying 404. Yeah, what that meant is object not found. The web page is not found. So 404, that status comes with a meaning. Okay, so we define also the semantic of some of these code words. Now, this is really nice to send code words because you use few number of bits instead of sending longer English strings. Okay, so meaning of the information in the fields. Now, of course, right, this is almost like defining a language. Yeah, the rules, the timing we send the message, and when we receive a message, what kind of message we generate next. Okay, so all four together, the types, the syntax, the semantics, and the rules of corresponding back and forth between the processes. That's called the application layer protocol. So each application defines its own application layer protocol, defining the messages it requires and the syntax, semantics, and the rules of exchanging the messages. Now, many of these application layer protocols are open, meaning if you just Google, you identify, for example, the World Wide Web's application layer protocol. That is actually called HTTP, and it's defined in one of these RFC documents. So these protocols are open such that if I want to come up with my own browser, because I know, hey, HTTP requests what the format should be like, the syntax, semantics, and rules, then I can write a browser such that it behaves just like the other browsers following the same RFC document. Same for email. Okay, so these open protocols are nice out there because each one of us can develop independently a new web browser, a new email reader, a new web server, a new email server. Now, many of the applications are commercial, owned by companies. So they do have their protocols, but they are not open. So these are the proprietary protocols. For example, Skype, we talked about using the hybrid model to communicate. It's got its own set of messages and syntax and semantics, but they're closed. It's hard to come up with our own client, Skype client, such that it works with the legit Skype clients. All right. As I mentioned earlier, designing a network application, there are 4 design elements. Now we have defined how one can design the architecture, 3 different flavors. And we talked about, one will need to implement and create such a socket to connect the processes, right, of the network applications. And then we just talked about how you define the messages and how the messages might be exchanged, okay, between the processes. The 4th is called the QoS, quality of service. Now, this last element, it's not really required, but you do want to consider quality of service or the user demand, okay, so that you will attract users and more of these users instead of creating in a network application, but no one is interested in using it. Okay, so quality of service, there are 4 kinds, meaning users, depending on the content they are sending, they are exchanging, they might like 4 different kinds of quality of service. Okay, and this video explains what these 4 quality of services are. Now, in order to know what is the right transport layer service for an application, we need to think a little bit more about the application we're designing. What is the nature of the content we're sending, and what the users might be expecting. The first criteria is called the data integrity. This concerns whether the data needs to arrive without any loss. The key word here is that if the apps are about sending text-based content, for example, a file, for example, a web page, for example, a text message, then users are expecting 100% reliability. If we're sending audio video, it's okay to have some loss. You know, think about speaking a sentence. If we miss a syllabus here or there, the listeners being human beings, we're intelligent. We can still make up the full sentences or make up for what the speakers want to say by looking at the context before and after the sentence. Second criteria, growingly important, timing. This is especially the case for interactive applications. So the key word here is interactive. Internet calls, live video sessions, or shooting games, interactive games. Users are indeed expecting low delay. Okay, and you guys know. Third is throughput. Okay, this is sometimes referred to as bandwidth requirement. Nowadays, we send multimedia content, audio, video. Text-based content, it does not require too many bits to send them, so it's not an issue. But for video and audio, we do need a substantial amount of bits per second in order to deliver them, so that the bits after recovery, okay, is in good quality. So if you compare video versus audio, the throughput requirement for video is higher and audio lower. Text, much lower. So we need to somehow guarantee a minimum amount of bandwidth in order for these audio-video communication to be effective. Text-based applications are elastic apps because there's no strict bandwidth requirement. The requirement is elastic. Fourth criteria, security. This is probably nowadays the most important criteria. Are the users expecting we are sending data such that we are protecting their privacy? Okay. So these 4 criteria together, we actually give it a special term. They are also called the quality of service. So before we can define what transport layer protocol we use, we need to think through what kind of quality we will be providing the application service. All right, so now at least you see that there are 4 different kinds of quality of services. Now, which kind you would implement or add to your network application, it really depends on the content the user demand. So it sounds a little bit vague right now, right? Data integrity, security. Next week, we'll start by giving you a few examples. For a particular type of application, people like data integrity. For another particular application, people like high throughput. And for many of the applications now, security. Okay, so next week, we'll start by giving a few examples, okay, demanding different quality of services. And the next topic is called transport layer. How do we provide these quality of services in our application? Yeah, you choose the transport layer protocol. Transport layer is 1 layer down. So you choose the particular protocol provided by the transport layer that offers that particular QoS. Okay, so that's the idea. All right, that's all the time we have. There are 2 questions at the very end. James was asking, can different computers share the same IP address? You know what? They better not, because if they share the same IP addresses, chances high that each of them will lose some of the packets. It really depends on how the network gateway, so when you are connected on the same subnet, the network gateway will try to explore what your Ethernet IP addresses is. Okay? And so by chance, the Ethernet address could be one of the machines, not the other. So if you are the one using the other Ethernet address, so IP address is higher level. There's another address called the Ethernet address. That's the hardware address. So the network gateway might miss your hardware address, and the packets get to the other machine that uses the same IP address as you use. Okay, so you might lose data. It's better not to. Okay, and that is a situation we say that we have an IP address conflict. Okay, and Jaden was asking, maybe VPN share the same IP address. You know what, Jaden, you're right. Guys, right? You guys are having a VPN connection to NTU, and then you access the PA server. So some of you might actually connect to the same VPN server. That way, you guys' connection will end up looking like they are all coming from the VPN server's IP address. And it feels like a few of you are sharing an IP address. But I wouldn't say that sharing an IP address is that way is a bad thing. But if you guys are sitting on the same subnet and you're configuring your IP addresses and you're using the same IP addresses with the other machine on the same subnet, then that is bad. Okay, good. So that's all the questions we have. And with that said, I will see you next week. Okay, goodbye. Go get lunch. Bye. Yeah, lots of stuff. Okay, bye.